Hello everyone, and you are on this talk about ultra-low bitrate generative compression of talking head videos to text. And I'm glad to welcome Pulkit Tandon, who is a PhD student in the electrical engineering department at Stanford University. Welcome to this our virtual studio, Pulkit.
Thank you for the invite, and thanks everyone for showing up for the talk.
Yeah, as well, I know that you also worked as an intern at Netflix, also worked on improving some video quality stuff. Is that correct?
Yes.
So, generally speaking, your last some time like year or so you spent with video compression algorithms. That's why you're here talking about that, and that's quite interesting topic since we are in this pandemic world right now. And the last few years, everyone is dealing with the video conference stuff or talking to Zoom with each other. And we mentioned at least some persons who are dealing with this mentioned a few issues, at least while doing that stuff. And we know it's not the perfect world yet, so there is a lot of gaps to improve. And one of that is kind of a way how to do that is just to compress video or audio at least to text and get back that from the text. Is that correct? Like, is that the topic you're trying to discover?
Yeah, did you already see my presentation? You just stole my motivation. I'm going to repeat the same thing.
Oh, oh, I didn't want to do this. Some spoilers ahead then. By the way, we do have this chat on the right side of the screen. You can text messages there, and if you want to ask something, Pulkit, about algorithms or something around that, don't hesitate to do so. In the end of the session, I will ask these questions, and afterwards we'll have a Zoom session where we can discuss more. So yeah, here we are to talk about this. All right, Pulkit, I'm not sure if you want to talk more before the session. I know we spent some time with configuration before that, like figuring out all the stuff for 10 minutes at least. So if you're ready
Yeah,
to go,
always the
let's do
case.
it. Yeah.
Yeah, okay, let's go.
Let's go.
Let me go full screen. So, should I start? Okay, awesome. Thanks again, everyone, for coming up for the talk. So, today I'm going to be talking about our work on Txt2Vid, ultra low bitrate generative compression of talking head videos via text. As Lev just introduced me, I'm Pulkit. I'm a PhD student at Stanford University. The large portion of this talk is basically joint work with a bunch of amazing people from Stanford, MIT, and UCSB. So let's just dive in. So videos are just like everywhere. Selva stole the motivation, right? So video streaming is 80% of today's internet traffic. Um, Surprise, surprise, COVID-19 led to an even bigger boom with tools such as Zoom seeing like 10x increase in usage. Uh, but unfortunately, the bandwidth of the world didn't scale as fast, and we still have limited access to the bandwidth. Just for your benchmark, a typical audio video call can take anywhere from 100 kilobits per second to few megabits per second. So video compression is really important, right? But isn't video compression already solved? We have these amazing set of codecs which have been developed over past few years from H.265, H.266 now, Google's VP9, AOM working on AV1, and there is a bunch of amazing engineers improving every aspect of it. So what's left? So one of the issues with all these traditional codecs is that they mostly focus on traditional pixel-based metrics. So metrics such as PSNR, um, etc. But humans don't really care about these pixel level details. And that's where the field started moving, I would say, at the start of this century, where we started looking more carefully into perceptual metrics, which is what humans really care about. So we had SSIM and now VMAP, which is like more of an industry standard. But if any of you have ever experienced working with these perceptual metrics, we know that there are already some issues with these perceptual metrics. So wait, what are these issues? Like, what's really different? So let's think about it for a second together, which is we as humans, when we talk about videos, what do we do differently compared to like these traditional codecs? So the first point is that we care way more about semantic details than we do about pixel level details. For example, here are two images of a giraffe, like two giraffes in a field. As you can see, like very clearly at pixel level details, they are extremely different. But as a human, when you see both of them, you basically extract very, very similar information. They look really similar uh, to you. And in fact, the second image here is almost 3 orders of magnitude compressed version of the first image. So, like, if you see, like, even though you lost 3 orders of magnitude information in terms of like pixels and what exact values they were, by just preserving the semantic details, you could still recover the original image very nicely. Okay, what else do humans do differently? Uh, so we have a shared vocabulary. We have shared vocabulary in the sense of we share the same words, and when we say certain words, very similar pictures originate in our head. So let me give you an example. So if I say blue chair, you might think of a blue chair like this, or like this, or maybe like this. Sorry, I'm not aware how chairs look in Russia, but I'm quite optimistic they look one version or the other of one of these pictures, right? Um, so as soon as I said blue chair, you have already filled a lot of pixels, sort of, so as to say, in a frame, and you knew what to expect. It wasn't really any random distribution of images. You had a fair bit of idea of what I'm going to talk about, and you could already picture it in your head. Uh, so, to summarize both these observations, uh, basically, humans share a lot of prior information about the world which we are viewing, right? It's not like any set of random values in a m cross n grid. It's very structured set of values what we are trying to view in the world. And like I said, like semantic details tell you what to expect when you see a video, and shared vocabulary tells you how to describe it. And all of these prior information can probably be used in much better to enable much better video compression, right? Okay, so the one of the works in a lab group exactly tried to tackle this from a purely, let's say, curiosity academic setting perspective, which is this work where we had two humans sitting at the two ends of the communication line. So you have a describer and you have a reconstructor. Your describer gets a target image, which now this describer wants to communicate to the reconstructor so that they can do image deconstruction. Uh, the way describer actually describes the image is through text instructions. So basically, describer has only access to like this semantic details. So they would say there is a giraffe, there is something else, right? And the way in this setup we extract the shared vocabulary is that both of the describer and reconstructor have access to the internet. So there are like plethora of images available on the internet. A simple Google search can give you a lot more images about blue chair. So that's like now kind of a shared human knowledge which we wanted to exploit. And so during the compression process, so as to say, so this is like compression and decompression at the same time, because the scriber is sending these text instructions to the reconstructor to regenerate the image. But then at the same time, the constructor is actually generating the image, and the describer has access to the feedback from the reconstructor. So this is not very different from the standard codecs, where when you are actually decoding, you have access to already like the information of previously decoded blocks in a frame, right? Uh, so again, to summarize the setup, we have two humans, so there is no machine, which are who are trying to communicate about an image. The describer only gets to communicate through the text instructor, its text instructions to the reconstructor, and reconstructor has no idea of this target image. The describer also gets some feedback from the reconstructor. For example, they can see while they are reconstructing how the image is coming up. And both of them have access to the internet, so as to kind of highlight the shared vocabulary aspect of things. So maybe let me show you the whole setup in bit more detail. So for example, for the same giraffe image, your describer can send a link saying, okay, get some grasslands. And the reconstructor can get a standard grasslands. Then the describer comes back and says that, okay, try some transformation. There is a fence, elongate it a bit, only focus on the vertical, so on and so forth. So now reconstructor can get a fence, they elongated the fence part a bit, and then you're only focusing on the vertical, and so on and so forth. So now you can keep describing that, okay, I need to change these things in the image, and your image can become more and more detailed. So yeah, so like just going through this whole process, describer is only transmitting the text, and reconstructor is trying to take this text and reconstruct an image. So this is the whole setup. And let's see the kind of example output, the kind of compressions you can get using this setup. So on the left, I have a original image. So this was like the uncompressed original image, which was roughly 5 megabytes of two giraffes in Africa. And then on the right, there are two versions of the same image, which are 1700x times, so 3 orders of magnitude compressed compared to the original image. And if you see, like, one of them clearly looks much more similar to the original image, even though the details are much more distorted. Whereas in the other one, you have lots of messy compression artifacts sitting there. And indeed, the first one was basically generated using the human compression framework as this. Whereas the second was generated using WebP, which is a very one of the state-of-the-art image encodecs. Both of the point to note is that both of these images are roughly the same size. In fact, WebP is slightly larger than the human compressed. But if we do a subjective study, like ask multiple humans to rate which of these two images actually look better compared to the original source, we saw that like humans on average rated the first image higher than the second image. So this is like one concrete example of how you can use the next generation, like of how you can use like how humans visualize videos in a practical setting, right? Okay, so now let's change gears a bit. So the setup which I described previously was a toy setup, right? Like it's clearly not implementable for as is. It's not really implementable in a practical setting. So there was no machine. There was a human reconstructor actually trying to get instructions and use it to decode, which is obviously not reproducible, and there are other issues. But it really highlighted like the limits of what we can do if we also include like various human aspects into compression. And the punchline here is the punchline here is basically you can get like orders of magnitude improvement in image quality than where we are as a tech currently, right? So excuse me. So let's ask a different question now. So like, which is like, how do we generalize the previous setup, which I told you, which tried to take advantage of these human properties, to some realistic video compression scenarios? And this is like the meat of the talk, which I'm going to be talking about today, which is the Txt2Vid framework. So let's talk a bit more about it. Okay, so as Clef clearly saw this slide and stole my idea, but basically we have been living in this COVID world, trying to connect to the other person over Zoom, and we have been in this modern rendition of Alice and Bob, where Alice is trying to connect to Bob using Zoom, and like you have Alice reaching out to Bob saying, "How are you doing?" Bob replying back, "I'm doing great. What about you?" But Alice is like, "Oh, your stream is freezing, Bob. I can't really hear you." Right? I'm sure all of us have been in this situation probably once during past 1.5 years. At that point, Bob would come back and say, okay, let me try switching off my video. Can you at least hear me now? And Alice goes, yeah, I can at least hear you, but I just wish I could have seen you while we were talking, right? So a very standard situation, at least for me, and I trust for many of you in the audience. Okay, so the question which we thought about after being stuck in these situations so many times was, wouldn't it be nice to have like audio video calls at lower bandwidth? And as I just demonstrated to you guys with the previous project, like if you are transmitting video, if instead of videos, if you are transmitting text, there is an 2 to 3 orders of magnitude bitrate advantage. So the y-axis here is bitrate. It's a toy schematic, which just shows that the typical video or audio streaming takes 2 to 3 orders of magnitude higher bitrate compared to text. So what this basically says is that going from videos to text, there is 100 to 1000x compression opportunity. So what do we do about it? So we ended up asking a question, which is, can we compress the audio video content generated via just webcams to text? So as you might imagine, like compressing from videos to text is fine, but decoding text to videos in an arbitrary situation is a really hard problem. Um, so we curtailed the domain space a bit, and we asked a more specific question, again, like similar to the Zoom setting or webinars when you are hearing to talks such as this, where you can ask the question that can we compress just the audio video content which is generated via webcams to text and then recover it. So cool, the question sounds really nice, but you would come back and ask me, hey Pulkit, like how do we even know if we are like, how do we measure, right? Like, sure, you can compress to text and give me a very bad quality video at the output. Is it really useful? So exactly. So we need some way to quantify, right? Like whether what's the distortion metric in our case, right? So bitrate is not the only thing. So again, repeating from what we had previously, the traditional focus has been single video pixel or single audio sample, and you focus on things like PSNR. Um, the recent trend is more on perceptual metrics such as VMAF, but unfortunately, there are no perceptual metrics for audio plus video experience combined. And naively thinking, you might say that video is much more important, but very surprisingly, that's not always true. Especially when you are working at extremely low bitrate content, the quality of audio in these calls becomes much more important than like the pristine quality of a video. So to tackle around these issues, we decided to say that okay, let's just focus on the overall quality of experience which a human gets when they are watching this audio video content, right? So our metric is purely subjective. We don't have any objective reference for it, and the subjective metric is very specific. Like we ask, like, what's the quality of experience of this command audio video? Okay. So if everything is clear so far, um, yeah. So the very specific question, very specific technical question, which we ended up asking in this work was, can we compress audio video content generated via webcams to text? So something which we have already discussed. Um, and recover videos with similar quality of experience. So you don't only want to just compress it to text, you want to recover videos with similar quality of experience, but similar compared to what? Compared to the standard codecs, right? And we are not comparing standard codecs like AV1 with 4K and extremely high quality content. Rather, since we are compressing it to extremely low bit rates, we are only comparing to standard codecs in a low bit rate regime because, as you might imagine, text is extremely low bit rate content. So, okay, just to repeat again, this is the question. So, if you understand the question, you will understand what we did next very well. So, repeating. So, can we compress the audio video content? So it's not just video, audio, video, generated via webcams. So situations like where I'm talking to you on Zoom or I'm giving this webinar, to text. So we are compressing it to extremely low bitrate text. And then you are trying to recover videos with similar quality of experience when you compare it to standard codecs in a low bitrate regime. So this is the question which we asked in this work, and not surprisingly, we answer it in yes. Otherwise, I wouldn't be giving a talk here. And so let me show you two videos now. One generated through standard codecs and the other generated through Txt2Vid framework. And let's see if you guys can guess which video was generated using which method. So here we go. This is the first video.
Hello, I am going to talk about banding artifacts. Banding artifacts are artificially introduced contours arising from the quantization of a smooth region in a video.
Okay. And this is the second video.
Hello, I'm going to talk about banding artifacts. Banding artifacts are artificially introduced contours arising from the quantization of a smooth region in a video.
Okay, let me replay both the videos for you. So in case you weren't able to hear it properly the first time. So again, we are not focusing only on the videos, but a combined audio-video experience.
Hello, I am going to talk about banding artifacts. Banding artifacts are artificially introduced contours arising from the quantization of a smooth region in a video.
Okay, and let's play the second video again.
Hello, I'm going to talk about banding artifacts. Banding artifacts are artificially introduced contours arising from the quantization of a smooth region in a video.
So okay, at this point, I'll pause here for 10 seconds maybe. And unfortunately, we can't have a show of hands, but like people in the audience, like I would like you to guess which one of these two videos was generated using a standard codec and which one was generated using the Txt2Vid framework. Cool. I think people have some guesses now. Let's see if your guesses are wrong or right. The first video was generated using Txt2Vid through 100 bits per second text stream. So note, it's 100 bits per second, which is sort of almost unprecedented in the video compression world. The second video, on the other hand, was generated using a standard codec, so a standard video codec, which is H.264, one of the most widely used, and a standard audio codec, which is AAC, and was actually 100,000 bits per second AV stream. But if you see in terms of quality from a human perspective, both of them look very similar. In fact, we had a subjective study in which both of these videos, like people were interchangeably happy with either one of them on average. So this is like the punchline. So we could get like almost 3 orders of magnitude improvement compared to H.264. Again, I understand this is not state of the art, but one of the most widely used video codec and AAC at approximately similar bitrate, similar quality. And moreover, we could get like just 100 bits per second text stream, which is like, so currently we can't even deliver videos at that bitrate. So if you are on the same page as me so far, let's now talk about like, how do we do this? Like what's the approach? Okay. So when you're doing audio video streaming, the conventional approach is you start from a sender. You encode the video and audio stream separately. So you will have something of the order of 1 to 5 kilobits per second audio stream and a 10 to 100 kilobits per second video stream, which is then combined at the receiver end and you get a video on the other side. So in Txt2Vid, we take a different approach. So in Txt2Vid, during typical operation, you are only transmitting text. So you use a speech-to-text operation to convert whatever the person is speaking to a text. You append it with some user ID as an identifier of the person who's speaking, and you basically transmit this package. But during once in the lifetime of communication between person A and B, we actually send a driving video, which is encoding the prior information about a person, right? So in these webcam videos, there isn't much really changing. You don't really need to send every pixel accurately. Instead, you could just like capture like the large scale features, the semantic features which are there in this video, which is a person really sitting in front of the camera, right? So once during the lifetime, we send a driving video, which is a really short clip, a 30-second clip with user ID to the decoder, so that like we know like for which user this clip is. So again, think of it as when you are downloading Zoom. At that point, or when you are talking with the person for the first time, at that point, you can already send this video. But then during regular communication between person A and B, like whenever we are connecting multiple times, you are only transmitting text. You are not sending the driving video. So then the decoder receives this text, use text to speech to convert it into speech, and then does what we call lip syncing with the already sent driving video to generate the final video, which is then obtained by the receiver as the final output, like the kind of output which I just showed you. So, like, there are two really important advances in technology which actually enabled a work like this. One is a high quality text to speech, right? So again, if you recall the videos which I showed, the voice wasn't robotic voice or a mechanical voice. The voice which you heard was very similar to my voice. And this has been enabled by latest advances in machine learning, where you can do a very high quality voice cloning of a person. And then the second machine learning model, which we are using, like the second advance, is lip syncing. What lip syncing does is basically it syncs the lip movements to the audio. So the input for this lip syncer is like an audio and either a video or a frame of a person. And then what lip syncing does is basically it makes you feel like as if the person is actually speaking that audio. So both of them are like actually high quality. Both of them are recent advances, like to so as to be able to produce high quality output. And a pipeline basically writes on these modern generative models to achieve like the kind of quality which I was just showing. Okay. If I hope everyone is on the same page. If not, I can also pause here for a second and take maybe one question from the audience. Because next we'll get into the performance evaluation. So I just want to see if everyone is on the same page.
Sure. I think I only have a question. Maybe it's kind of more about security, or like not about the engine, how it works. I know it's probably a little bit more complicated as it seems to be. I mean, this lip syncing algorithm, but I have one concern here. Like, we don't know what the black box is, how it actually processes the text which generated through the audio from the original audio. But is there any chance we can, put another word in the which will synchronize with lips as well, but we can add some more adjustments to the text, and you won't be able to recognize it was a machine learning algorithm with a pure original audio, or it was slightly modified during the processing time.
No, all excellent questions and thoughts. And I also see someone, Max, is asking on the chat about emotions and security and actually putting someone else's voice when we are speaking. So I'll talk all of them about it in a second, actually.
Sure.
So in the next part of my talk, I'll touch upon all of these points, and all of them are like really great thoughts. But yeah, so I would like to take one question, which is deepfake. Essentially, this is a sort of deepfake technology, and we all know there are like security risks to the deepfake. But I think one aspect which has really not been studied as much about deepfakes is how we can actually also use them for positive use case. So far there is this environment of fear around deepfakes, but this is like, I would say, one of the works which try to use this deepfake technology for something good. So yeah, I'll also touch upon it briefly at the end. But I guess, okay, so it seems like everyone, or at least the attendees who asked the questions, at least are on the same page as me with regards to the pipeline. So maybe we can move to the performance evaluation. And again, all of them are great questions. I'll talk about them at the end of the talk. Hopefully, they are answered through the talk. Okay, so let's continue. So so now I described you the pipeline. Let me talk to you a bit about how we actually evaluated this engine. Um, so like I said, there are two critical components for text-to-Vid decoders. One is text-to-speech and the other is lip syncing. So for text-to-speech, we use something called resemble.ai. And the salient feature about resemble.ai is basically you need very few samples to do voice cloning. So basically to generate a voice artificially, which sounds very similar to your original voice. For example, in the video which I showed of me, I just had to record 50 short sentences, like single line, 5-second clips, so as to be able to reproduce a voice which looked like that. And again, I didn't use any studio level equipments or anything. This was all done at home. So you can already see where the tech is at with respect to the text to speech. Similarly, for lip syncing, we used an open source tool called Wave to Lip. And the idea of Wave to Lip basically is, like I described it, syncs the lip movements to the body with the audio. And the salient feature about Wave to Lip is that it's actually able to do it very nicely for videos in the wild. So you can take any random video with a person's face in it, you can have some soundtrack, and you can generate an audio video clip where it appears as if the person is speaking that audio. Again, all those security concerns and everything, we'll touch upon them in a bit. Okay, so for evaluation, we actually needed some sort of data set. We didn't find any data set which fit a bill. So we ended up creating our own data set. So in our data set, we have 6 contents. So 6 different people in very different lighting conditions, different genders, different ethnicities, a lot of variation basically in these videos, talking about some technical content in a short clip. And then you take this clip and you do 2 things. You generate set of benchmark videos, which are basically generated using a standard codecs. And you also generate this compressed text transcript and use it to decode these videos using Txt2Vid. The way we generate benchmark videos, we actually were careful not to overstate our claims. So we basically used sort of 2 settings. In one setting, we had H.264 encoded videos, because H.264 is one of the most widely used video encoder, along with AAC audio encoder, which is both most widely used as well as the state of the art. So this setting is sort of saying typical use case on the internet today. But we also compress these contents using AV1 encoded videos. So we also use AV1 video encoder as a state-of-the-art video encoder along with AAC. So we basically have 2 sets of videos. One, let's say, which are more widely, more commonly in distribution, and also the set of videos which are more like state-of-the-art, compressed at this low bit rates. So okay, we take this data set, and like for evaluation, I've been saying we focus on quality of experience. So we ended up doing a subjective study. So this work was done during peak of Corona earlier this year. So the way we couldn't do experiments in lab, so we ended up performing a subjective study using Qualtrics and Amazon MTurk. And so basically, we had a survey which we made like Amazon MTurk workers take, and this survey basically consisted of prompts like this, like what's shown here. So a participant would see 2 videos, like a video on the left and a video on the right, and basically they will be asked to watch this audio video, and they were asked like select the one video which you prefer. And so one of these videos was taken from the benchmark set, so encoded using standard codecs, and the other video was basically the video which was decoded using Txt2Vid, starting from just text. And the order was shuffled, like everything was randomized. The order in which you show these videos, the order in which they actually appear in a frame, and all those things. And we ended up having a total of 240 participants and roughly 40 subjects per comparison. So for each content, for each setting of the standard codec, so we had multiple different QPs or multiple different quality encoded audios and videos. For each of these setting benchmark video, and for each of the Txt2Vid video, we had roughly 40 subjects per comparison. Okay, so this basically describes the experimental setup. So maybe let's look at the results which we got through this, right? So okay, here I'm first going to show you comparison against H.264 and AAC. In this plot, I have 6 different subplots, which basically correspond to the 6 different contents, 6 different people speaking something entirely different under different lighting conditions, all those things, right? For each content, maybe let's focus on one content now, which is, let's say, me speaking something. So for this content, the y-axis shows the user which are preferring Txt2Vid method. So higher the number here basically says larger number of users, larger percentage of users actually like the Txt2Vid decoded video than that particular benchmark video. Similarly, on the x-axis, we have ratio of standard codec and Txt2Vid bitrate, which is basically the compression ratio. And if you look carefully, the x-axis actually is going from 100 to 3000. So it's not 1, it's 100 to 3000. So like the points which I'm plotting here are already like 2 to 3 orders of magnitude compressed. And the Txt2Vid points are 2 to 3 orders of magnitude compressed compared to the standard video codecs. And then we are asking users to compare for the quality of experience. Okay, so just to summarize, if I spoke too much, too fast, the x-axis, as you go towards the right, compression increases. The y-axis, as you go towards up, the Txt2Vid's preference increases. So ideally, we would like more points on the top and as much right as possible so that you can get more videos which had better performance for Txt2Vid at a higher and higher compression ratio. The blue line, which you see in these plots, is basically the ISO quality of experience line. So basically around this line, users were on average confused. Like some users picked the Txt2Vid video, some other users picked the standard codec video. So roughly, basically we get, for example, for this content, we get around 1000x compression at ISO quality when you compare Txt2Vid videos with the benchmark videos. And yeah, sorry. And there is obviously some variation across the contents because of the kind of speech you are able to reproduce, just the diversity in the videos. But even then, like I would say on average, we were able to get 2 to 3 orders of magnitude improvement. So for example, for this content, we are not performing as well, but still like we get like around ISO quality at like 2 orders of magnitude. Actually, for all contents, we get like this benefit other than the content too, just to be accurate about our study. But so in our subjective study, we also asked users to give us comments on what they preferred during the video, what went wrong, what went right, if they had any thoughts during the comparison. And what we found was like for this content, actually, the voice which we generated using text-to-speech was very robotic. And that's why the users were actually immediately able to identify that, okay, there is something amiss for this particular one compared to the other one. So yeah, so like if you don't have a good quality text to speech, like your performance might suffer. But then again, still a non-negligible fraction of people prefer text-to-vid video, even at 100x lower bitrate compared to standard codecs. To highlight, this is the same video which I showed. So somebody had asked the question of emotions. So yeah, emotions are currently missing in the pipeline. Even then, at the bit rates at which we are dealing with, people prefer text-to-vid videos because we are just working at 100 bits per second. So you have to be um, you have to keep that in mind when you are actually comparing this pipeline, right? Okay, so roughly 3 orders of magnitude at ISO quality for H.264 and AAC. And similarly, you can look at results for AV1 with AAC. Obviously, we expect to get lower improvements because AV1 is much, much, much better than H.264. And that's what we see. So it's again the same plot. I have 6 different contents. Y-axis is the higher y-axis is like more people preferring text-to-vid. More on the x-axis is a higher compression ratio. You can see the axis is now changed. So axis now goes from 100 to 400, no more 3 orders of magnitude advantage, but we still get around like 2 orders of magnitude compression at ISO quality using this subjective study. So yeah, so I guess the key highlight is like we at this extremely low bit rates, like we are talking about 100 bits per second text to vid video and around 10 kbps to 1 mbps generated videos, audio videos generated using standard codecs, we could get almost similar quality experience on the other end when a user was viewing it, which drastically changes the landscape of where you can deliver these videos where it wouldn't have been able to before. So, okay, these are my results. But so far, these results were basically mostly focused on the decoder. So we only focus on the decoding aspect. I haven't really shown you how it looks for a streaming case. So this is when you can think of it, whatever results I've shown so far, as if you are storing a file and playing it on your end. Or you have, let's say, my talk recorded, and then you send just the text transcript of my talk, and you use it to recover whatever I've been speaking on the camera to just recover my expressions, right? So let me also show you a streaming demo. As most of you know, streaming has much higher latency requirements. And even though we don't meet it, I just wanted to show that we already have code available which does something like streaming. So again, like the streaming is just a proof of concept. It's nowhere close to production level. This was just a first pass at it, like how well can we do if we were communicating using this. And in this video, you will see me using a text-to-vid pipeline, and I'll be communicating using text. So on my end, I'm a sender. I'll be sending text through the terminal. And on the receiver end, my friend who will be receiving this video will use text-to-vid to decode and actually generate the final video. Okay, let's see. So Shubham is going to receive this text and then use the text-to-vid decoder to decode the audio video from the text. And so yeah, so let's try it out. So I'm going to mute myself now so that you don't hear the audio twice.
Hello. How is it going? I hope it's going good. This is a demonstration of our streaming pipeline. I hope it works. I think it did. Awesome. Talk to you later then, bye. So yeah, so this was a demonstration of streaming. Me and Shubham were at different physical locations, and we were using this text-to-vid framework to actually regenerate. I was sending text on my end as if I was chatting, and then Shubham was basically talking to me.
using this Txt2Vid recovered framework. So great. I think I have talked a lot about the positives so far, but the streaming demo, I'm sure for the technically inclined, clearly brought out some limitations of the current pipeline, the current implementation, and maybe it's good to talk a bit more about them in detail. So the first set of limitations are around the pipeline. So as you could see, there was like around 5 seconds latency, which was also slightly variable because of how we implemented the TTS and transmission of text, which is not ideal. And then there are these quality of experience issues like, like, wouldn't it be great if we could also add emotions or body gestures, right? Like all these things. Uh, Again, like, so for latency, this is not a fundamental problem. This is just like a first implementation, and like I'll share a GitHub link with you guys at the end of the talk, and I would like to encourage all of you to check it out and help us improve our implementation, right? So it can very easily use better software engineering. It was done in an academic environment. Um, we haven't used any real-time protocols for streaming. So the decoding which I was showing you was actually done using FFmpeg, just stitching and playing using port forwarding. And then for the quality of experience, we are thinking of multiple things. But one of the things which you can do is like you can also have custom models for adding emotion. So you can imagine doing text sentiment analysis on the text which you are sending and using it to also include emotion in the sort of deepfake generated video, right? So none of these are like fundamental limitations. These are just like limitations as they stand. Then there are some more limitations on the decoder side. One is computational complexity. So we are using these deep learning models, which basically requires GPU on the decoder side, which completely beats the purpose because I'm giving you this extremely low bandwidth output. But then if you need GPU on the other end of the side, you might be a bit more critical about it, right? And then there is currently a reliance on cloud-based APIs, which is like TTS. For TTS, we use resemble.ai. But again, none of these are like fundamental limitations. For computational complexity, there is like continuous improvements in hardware. We also have like more and more open source deep learning models, even though like resemble.ai is state of the art in 2021 and it's a startup. It's not hard to imagine that by 2022 2023 we have similar quality open source tools available, or maybe even better, at which the tech is developing, right? And then you can also think of like a lot of these work on edge computing, like model compression, model efficient model for like doing the same things. And finally, computational complexity is not a completely deal breaker because at times you might not have access to the bandwidth, but you might have access to the compute. Think about when you are traveling to a remote location with your family, going for a hike, like you might, or not a hike, but probably a bad example, but maybe let's say a vacation, and you are carrying a laptop on you. You might not have access to good bandwidth all the time, but you might have access to laptops. So it's a continuous work, but again, it's not a deal breaker and something which we are looking into right now. Finally, as brought up even during the middle of the talk, there are like ethical and privacy concerns associated with this work, particularly like whether a tech like this will be socially accepted. What's like the safety? I can make a person speak anything, or I can have any person speak anything else, like all the standard limitations of deepfake. Actually, Russia, of all places, is much more ahead than the world on use of deepfakes for practically and socially useful settings. For example, there was even an advertisement featuring Bruce Willis, where the Bruce Willis was generated using deepfakes, right? So what I want to say here is that like this is something which we definitely need to come together and think as a community on how we can start using these deepfakes for better use instead of just worrying about like all the misuses which are already out there. Um, and for particularly safety with tech, actually, we have thought of something where you can limit the usage of generative models only during call using some sort of an encrypted key, which the sender has to confirm that, okay, right now my text-to-vid decoder can actually has permission to use my voice and my face on the receiver side, right? But then again, these are like important issues, and we need community coming together so as to be able to resolve them. And in fact, we have a workshop in CHI next year, which is basically on positive uses of deepfakes. So if you are interested, I would encourage you to attend this workshop and bring forward your criticisms and ideas so that we as a community can see how we can use it for the better good. Okay. Finally, I just want to highlight like all of these are future works, something which we are working on. But typically, the emotion is the one of the things which comes out very often, and that's something which we have already started looking at. So in future, you can also think of like adding key points for both body pose and face. So if you think about it, in these talking head videos, we have already covered, let's say, the first order approximation, which is a person should look like as if they are really speaking what they are speaking, right? The next order of magnitude is actually to capture the hand gestures, like which I have been doing continuously, right? The body pose, the face movements. And one way to integrate it, which we are thinking, is if we can combine some sort of key points along with text for basically doing a first order of body pose and face estimation. And this is a work from a lab group where, sorry. Sorry, it should play a video, but I'm not able to play it. Let's play. Yeah. So what you see in this video is you have a sender on one side, Roshan here, and there are key points extracted from his face and its body, and only those key points are transmitted. And then on the receiver side, you basically have a cartoon trying to reproduce the same thing. So you can see, like, as he's doing his body gesture movements, you could see it as he's opening his mouth and doing all these things. You can see it. So yeah, so this is also a very, very recent work. And in fact, this work was followed up by NVIDIA's Maxine, where they actually they had the exact same idea where they extracted the key points, but now they had a more realistic keyframe. Instead of avatar, you had like an actual person, and they had much higher complexity neural networks to actually reconstruct the video on the other end finally. So yeah, so this is something which is like has been picked up by industry. But I again want to highlight that Txt2Vid, as it stands currently, is 100 times more bitrate efficient. So like this keypoint technology, you still need around 10 kilobits per second of bitrate, whereas Txt2Vid, you could get anywhere down to 100 bits per second. So the key point here is that, the key point for key points is that you can try and include it in the Txt2Vid framework, but you're gonna pay the price in terms of bitrate. And ideally, we should get a rate distortion curve where, like, if you are in an extremely constrained situation, you just send the text. But if you have more access to bandwidth, maybe you send the key points so that you can also include the emotions and face movements and body movements and so on and so forth. And obviously, on the other end of the spectrum, if you are watching Netflix, maybe you want 4K and you have much higher bandwidth at your home. So this is the whole spectrum which we are thinking of and working on right now. And yeah, okay. So on to the final slide. So thank you for your attention so far. What I want to highlight is that there are lots of potential applications which a tech like this can open up. So obviously there is this whole communication thing during COVID where you don't have access to good bandwidth all the times, but you would still like to talk to your loved ones sitting across the continents. There are also situations of where you would like to communicate from remote terrains where you might have a lot of decoder tech available, but you don't have access to bandwidth. For example, if Elon Musk is able to send us to Mars soon, maybe you don't want to send 1 megabits per second audio video call for every person on the Mars. At that point, like a tech like this could prove to be very useful, or if you're stuck in a desert region, right? So yeah, so there are all these remote talks. There is also the decoding aspect of Txt2Vid. So for example, you can just use the decoding aspect to actually get a text transcript of a lecture and then have your favorite instructor let you teach it. So it's like, as somebody asked in the middle of the talk, it's like you can actually put words in someone else's mouth. So I can have a physics lecture, I can have Einstein actually deliver that lecture in his voice and his tone. And that's something which I might find more engaging. And related, Slev and I were talking just before the start of the talk, and you can also imagine real-time transcription using a technology like that, where you can, as we know, like tools like Google are really good at translating, let's say, English to Russian. So we can have this text transcript sent, converted into Russian, and then have a text-to-speech model trained in Russian, so that, like, as I'm speaking this in English, for the people in the audience who maybe are not that comfortable with English, they can get a live transcription of things in Russian. So yeah, so there are like lots of potential and cool applications at the horizon. And again, I would like to say it's a first implementation. It's nowhere near polished. So I would invite all of you to like get involved. Please contribute to the code. The code is open source on GitHub. Like feel free to take the code and like extend it to various different applications, or like improve it on various limitations which we touched upon. If you have any thoughts and idea, please feel free to reach out to me so that we can work constructively. We can take this tech constructively forward. Finally, there is also a technical report on archive. So if you want to read more technical details about this work, you can just go on the archive and read it. Yeah. Thank you. That's my talk. Thank you for your attention. Happy to take questions.
Yeah, thank you for your talk.
Thank you for your talk.
It's very interesting topic. I think we had few questions in the chat, at least remember them. First one is from Max Kalesin. It's actually about the emotions, about the part which you were talking about in the end, I guess, about losing the emotions while you're reconstructing them from. You cannot reconstruct the emotions. It's pretty hard from the text as well. So I think that actually.
So we have multiple ideas there. I actually talked about one of these ideas. So if you are okay going above a bit of the bandwidth, let's say I have a bandwidth budget of 1 kilobits per second instead of 100 bits per second, maybe you can also integrate these face key points along with the text to get those emotions out. Or actually, there is another idea. Another idea could be you can use emotion detection. So you can train. So far we were using the already existing models, right? But you can also train custom models to actually add emotions, which all you need to do, not all you need to do, but at a high level, what you need to do is basically extract emotion from the text. So text sentiment is something which is very well understood, and use this sentiment to actually have a custom model where you also change the face to like happy, sad, and all those things. And I'm happy to point you to some literature. It's already something which people have looked into.
Yeah, you're right. And I think the next question is also about some cases when it's hard to get the emotions or any details from the face recognition. It's Oleg asked, what about the case when lips are not visible, since we are living in this COVID time now, and there are masks on the faces sometimes, and also people can switch off the camera as well, I guess. Is there any workarounds? Have you thought about that?
Yeah. Sorry, I couldn't get the name of the person who asked the question,
Alec.
but Alec. Okay, yeah. Thanks, Alec, for finding a really nice loophole in the work. Like, yes, it's not designed for people wearing masks while talking, but I think if you are wearing masks, at that point, like, I think the primary information is your body movements. Really, it's not even emotions at that point. And for capturing body movements, there is obviously like this keypoint work, for example, in Media Maxine, and we work by a lab group from Roshan. But overall, I think at that point you have to shed more bits. I don't have a good idea of like what do you even want the text to do in that situation. But then again, I think it's a very very corner case situation. I probably never want to wear mask while giving a talk remotely. So yeah.
Yeah,
And
there
if you are
could be.
wearing a mask, if you are wearing a mask, I would really encourage you to do in meeting for like meetups in person. Sorry, meetups.
Sure thing. Yeah. Yeah. Thank you very much for your talk. We are kind of out of time right now, I guess, and we can move to the discussion zone, to the Zoom session, and we'll talk a bit more then with you folks. So don't hesitate to join the Zoom session. I know it's kind of late time in Russia right now, but yeah. Anyways, looking forward to you. Thank you for the whole really nice conversation and the talk, Pulkit. It's very interesting approach you described, and I think everyone is moving in the right direction with this compression algorithms and machine learning algorithms as well. Thank you. It was a pleasure to talk to you.
Yeah, thank you so much for inviting me for this talk, and I would also like to thank the audience for really thoughtful questions and comments, and happy to continue the discussion on Zoom.
Yeah, please join the session and see you around.